Hi, in the previous video we reviewed the development of the theory of plate tectonics. We spoke about the mechanism that drive plate motions and introduced the type of plate boundaries. This video is the second part in a series of two dealing with plate tectonics. In this particular video we will review the three types of plate boundaries and learn about the morphological feature resulting here in the surface. Lastly, we will discuss the implications of plate tectonics in the evolution of land masses distribution in the past and today. Enjoy it and don't forget to like, share and subscribe. When two adjacent plates move away from each other, they constitute divergent plate boundaries. They can occur in both the ocean floor and also within a continent. When located in the sea, they occur along the crest of oceanic ridges and could lead to seafloor spreading. When they occur in the continent, they may form rift valleys as continents break apart. Convergent plate boundaries and subduction, on the other hand, contribute to the recycling of lithosphere materials as the continuous production of new seafloor in the area along the crest of oceanic ridges and adjacent plates spread apart. This results in the formation of new oceanic lithosphere between them that progressively gets older as we move away from the spreading center to be destroyed and begin a new cycle. The last type of plate boundary is the transformed plate boundary, where neither production or destruction of the lithosphere is noticeable. Let's talk about these three types of plate boundaries in more detail. If we could drain out the water of all the oceans, a remarkable feature of the planet's surface would emerge very prominent. These are the oceanic ridges. They lie in the seafloor below the ocean waters, thus we cannot see them with our own eyes. Features such as the Mid-Atlantic Ridge, East Pacific Rise, and the Mid-Indian Ridge are those features. The global ridge system, exceeding 70,000 kilometers in length, constitute the longest topographic feature on the planet, representing 20% of the Earth's surfaces. If we drain all the water from the oceans, it will look like the seams on a baseball. Ridges are quite prominent on the seafloor because they are high. The crest of the oceanic ridge is commonly 2 to 3 kilometers higher than the adjacent ocean basins. They are very wide. Ridges vary in width from 1,000 to more than 4,000 kilometers. They are also very active. Here, new crust is formed and displayed intense volcanism, for example. Following World War II, the mapping of the ocean floor led to the discovery that along the oceanic ridge systems, new oceanic crust is created as crust pieces drift apart, forming an elevated valley. The mechanism that operates along the oceanic ridge system to create a new seafloor is appropriately called seafloor spreading. This mechanism is very slow. Typical rates of spreading average around 5 centimeters per year, roughly the same rate at which human fingernails grow. Comparatively low spreading rates of 2 centimeters per year are found along the Mid-Atlantic Ridge, whereas spreading rates exceedingly 15 centimeters per year have been measured along some sections of the East Pacific Rise. Given enough time, these seemingly insignificant seafloor production rates are enough to have generated all the Earth's ocean basins within the past 200 million years, a fantastic example of the uniformitarian approach where small continuous changes can lead to significant transformations on the Earth's crust, like the breakup of Pangaea and the opening of an entire new ocean basin. In addition, something quite remarkable happens here. As we move apart from spreading centers on the seafloor, the older, cooler oceanic lithosphere increases its thickness and rigidity. Thus, the oceanic lithosphere gets progressively older and reaches its maximum thickness in areas farther away from the spreading centers where it is generated. As the newly created seafloor cools and contracts, increases its density and sinks lower into the mantle, resulting in an increased water depth away from the ridge axis. As water becomes deeper away from the axis, more accumulation space makes that more sediment pile up on top of the new oceanic crust, resulting in significant accumulations of marine sediment. We just discussed how continental rifting develops in the ocean, but we can also find divergent boundaries within a continent. This occurs when plate motions produce opposing tensional forces that pull and stretch the lithosphere. Due to the immense tectonic forces, it will eventually lead to breaking apart or rifting. When we stretch something, it gets thinner. Well, in this case it's the same. Stretching promotes mantle upwelling and broad upwarping of the overlaying lithosphere. Eventually, the broken crust will generate a low topographic relief, a sort of elongated depression called a continental rift valley that in some instances may be filled by an oceanic basin. Check out this amazing example. This is the East African African Rift, a crack in the Earth's surface that runs along parts of East Africa. Seen even from the space, it encompasses several countries along the entire East African Rift system. Today, it constitutes an example of a modern active continental rift, where the continents separate due to the tensional forces that have stretched and thinned the lithosphere. Therein, the majestic Mount Kilimanjaro, formed when molten rock ascended from the mantle due to the stretch and thinning of the crust that allowed molten material to ascend to form a volcano. The Rift Valley is fascinating because it gives us a modern analog of how new oceans basins emerge. This is because if rifting continues, it will become eventually a narrow sea. What is even cooler is that nearby, here in the Red Sea, we see this process at a larger stage. When the Arabian Peninsula split from Africa, the resulting basin is the Red Sea. We say that it is a modern analog because it gives us an idea of how the Atlantic Ocean may have looked like in its infancy following the breakup of Pangaea, a topic we discussed in the video on continental drift. I will place the link in the description below. Convergent boundaries can form between an oceanic plate and one continental plate, two oceanic plates, or two continental plates. We have remarked that at the oceanic ridges, new lithosphere is constantly being produced. At this stage, it is important to reflect on the following aspect. If a new lithosphere is constantly being produced on the planet, why does its total surface area remain constant? There has to be a mechanism whereby it is destroyed to be created again. In other words, a sort of cycle. Well, in this case, that is what happens. The crust gets recycled. A balance of crustal material in the planet is maintained because older, denser portions of the oceanic lithosphere descend into the mantle to be destroyed in convergent plate boundaries, so-called subduction zones or destructive margins, at a rate equal to seafloor production. Therein, oceanic lithosphere will subduct to be destroyed at great depths due to their differences in composition. The denser oceanic slab sinks into the mantle. An amazing feature of the planet is the result of this process. The trenches, deep oceanic topographic depressions, produced as the oceanic lithosphere descends into the mantle. They are stunningly long, deep, and quite dark. Along the west coast of South America lies one of them, the Peru-Chile Trench, as much as 8 kilometers deep and measuring more than 4,500 kilometers long. It is a gigantic scar in the planet's surface, but it is not the only one. In the western Pacific, the Mariana and Tonga trenches are even deeper. Here, a slab of oceanic crust descends into the mantle at much higher angles, as here the oceanic lithosphere is older and cooler, therefore denser. Perhaps one of the most impressive types of plate boundaries are the convergent boundaries, with oceanic continental convergence because of its resulting features. When a buoyant continental block converges with a slab of oceanic lithosphere, due to their differences in composition, the denser oceanic slab sinks into the mantle. Heat and pressure increase as the plate dives into the progressive hotter asthenosphere. Herein, fluids containing the subducting rock lead to some melting. This process is called partial melting and is very important in the rock cycles, as is thought to generate some molten material which is susceptible to mix with the unmelted mantle rock, or ascend again reaching the surface to form a mountain belt chain, or rather take a different path and solidify still at depth inside the crust. If this happens, the crust will be even thicker. The volcanoes on the Andes mountain chains are the result of the product of this process. They form from the subduction of the Nazca plate beneath the South American continent. This generates partial melting of the rocks that encounters the mantle. As a product of the increased temperature, this hot mobile material is less dense and slowly moves upwards to the surface, where it results in the majestic Andes mountains. However, much of this material never reaches the surface, making the crust even thicker. Note how they also constitute a bunch of volcanoes with a preferential alignment. Volcanoes like this, which are produced in part by volcanic activity associated with the subduction of oceanic lithosphere, are called continental volcanic arc. In North America, across the Cascade region, active volcanic mountains including Mount Rainier, Mount Shasta, and Mount St. Helens, extending into Canada, where it includes Mount Garibaldi, for example, constitute a good example of them. Here is one that I find quite fascinating. In some instances where oceanic land masses come together, one descends beneath the other. As with the subduction zones, volcanic activity begins, leading to the formation of volcanoes, not in the continent, but in the ocean. If this process continues, eventually a chain of volcanoes that appear as large protuberances in the seafloor will emerge as islands. The resulting resulting chain of islands that form as a product of this process looks like an arc-shaped alignment of volcanic islands. Thus, it receives precisely that name, a volcanic island arc, or simply an island arc. The Pacific Ocean is full of these examples. To illustrate this, let's check out this map. For instance, take the Aleutian, Mariana, and Tonga Island. They constitute very good examples of volcanic island arcs, located adjacent to the Aleutian Trench, the Mariana Trench, and the Tonga Trench, respectively. Okay, that is the Pacific Basin around the western part of an area that is so tectonically active and dynamic that has been named the Pacific Ring of Fire. What about the Atlantic Basin? Well, here, the Lesser Antilles Arc on the Caribbean Sea and the Sandwich Islands are also volcanic island arcs. How do they form? The Lesser Antilles, for example, is a product of the subduction of the Atlantic seafloor beneath the Caribbean plate. But the islands that make up the Lesser Antilles are not the only ones. Located within these volcanic arcs are also the Virgin Islands, as well as Montserrat and Martinique, host of the well-known volcano, the Firi Mount Pelée. However, volcanic islands may have a much more complex history and may involve several events. At this stage, it is important to mention that Japan, Indonesia, and the Alaskan Peninsula technically are also island arcs. It's just that they are much more complex and are the product of a longer history of build-up by the same processes that include the formation, likely of earlier episodes of subduction. This last type of convergent boundary results when two land masses of the same composition and same density converge towards the margin of each other because of the subduction of the intervening seafloor. This is the case of the continental crust that, due to its composition, is lightest compared to the oceanic crust, resulting in a continental-continental convergence. The resulting effects of the continental to continental crust collision is that the crust and the accumulation of sediments and sedimentary rocks falls and deforms, particularly along the continental margins where overall this process is more intense, resulting in a mountain chain. This results in the formation of a new mountain belt composed of deformed sedimentary and metamorphic rocks that can even contain pieces of oceanic crust. A good example of this type of convergent boundary is India, a collision of the subcontinent of India into Asia that began about 50 million years ago. The resulting mountain belt is the Himalayas, host to some of the highest mountains on Earth, including Mount Everest. During this collision, the continental crust buckled and fractured and was generally shortened horizontally and thickened vertically. The Himalayas is perhaps the most prominent example of this continental to continental crust collision. However, other major mountain systems, including the Alps, Appalachians, and Urals, form as continental fragments collided. The last type of plate boundaries are the transformed plate boundaries. These unique places are quite special because here the plates slide horizontally past one another, neither producing or destroying lithosphere. They were discovered in 1965 by Canadian geologist John Tuso Wilson, who proposed that these large faults connected two spheric centers, divergent boundaries, or less commonly, two trenches that are convergent boundaries. Most of them occur in the ocean floor, where they offset segments of the oceanic ridge system, producing a step-like margin quite noticeable due to a sort of zigzag shape. Here is one prominent example, the Mid-Atlantic Ridge. Notice how it looks like the outline of Africa and America? Well, that happens because that is the remnant shape of the original rifting that caused the breakup of the supercontinent of Pangaea. Most transform faults are part of prominent linear breaks in the seafloor known as fracture zones, which include both active transform faults as well as their inactive extension into the plate interior. Although most other transform fault boundaries are located within the ocean basins, however, a few cuts through continental crust. Two examples are the San Andreas Fault in California and the Alpine Fault in New Zealand. Along the San Andreas Fault, the Pacific plate is moving towards the northwest past the North American plate. Quite an amazing example here on the surface that offers a unique glimpse of the internal dynamics of our planet. Well, thank you for watching up to this point. I hope this video contributes to increase your admiration and amazement towards our planet and all its interconnected systems. Please let me know in the comment box which one you think is your favorite mountain chain and, most importantly, why. About me, I quite like two actually, the Appalachians in North America and a younger one, the Alps in Europe. Why? Because I like the gentle rolling hills in the Appalachians, the products of millions of years of erosion. And about the Alps, I like some of the valleys made in the last glaciation. They are much more younger mountains. And you? Please let me know in the comment box and I will do my best to answer all of them. Don't forget to like, share and subscribe, and I will see you in our next video. Ciao!